Welcome back. Today we're going to talk about sparse signal representations. In general, these look very much like what we've seen before. Namely, we have a y equals, and this time we're going to use a d for reasons that'll become apparent in a minute. We're trying to find another variation of solutions to this equation. The main difference for sparse representations is that we're typically given the vector y. And we want to find two things. One is a matrix D, and the other is the vector x. Now the key here is that x is sparse, meaning that most entries and I'm actually not going to use that notation because it'll get confusing with later. I'll just say most entries of x are 0. So, for example, we might have something like 0, 0.2, 0, 0, 0, 1. Might be something like that. Okay, so the other difference is that D is usually not a basis. Rather, this is a dictionary. So what is a dictionary? A dictionary is another word basically for a basis that is not a basis. In other words, we have vectors that span a space, but they're typically overcomplete, meaning that we have far more vectors than needed to span that space, and so there's going to be some linear dependence going on. Okay, so I guess for that to make sense, I should probably also note that D is R n by k. K is often called the dictionary size. And the elements, a common term for them is atoms. Let's see. Atoms or dictionary elements. Then, of course, this is going to be k by 1, and this will be n by 1. So, this is the basic problem they're trying to solve. Now, the difficulty here, we could come up with an x, for a given d, we could come up with the optimal x. But coming up with one that is sparse is a much more difficult problem. And That's problem number one. And problem number two is, well, where do we come up with the dictionary D to begin with? It's important that we design D intelligently so that it lends itself to sparse representations. For example, if we were trying to represent our signal maybe consisted of numbers, handwritten like that. This is two-dimensional, and we're talking about one-dimensional vectors, where at least one by k or one by n. So how would we relate this to what we're talking about? Well, we could vectorize this image. In other words, take every row or every column and string them all in together to make one very large vector. And although it looks like the spatial information is lost, all the information is there, and the mathematics can deal with it, whether or not it's easily visualized by us or not. So let's say we had a data set that had a lot of different numbers in it, like this, handwritten digits. And we wanted to represent these using some sparse representation, as we're talking about. Well, first off, it probably wouldn't make sense to have dictionary elements that were just nice, orthogonal, every dictionary element lit up a different pixel. Using that, we could create, of course, any number that we want. And in this case, we wouldn't use very many. We'd only use, for each number, those dictionary elements that corresponded to the actual digit itself and not the empty space around it. But it might make better sense to come up with dictionary elements maybe one looks like this, and another one looks like this. Well, why? It's because it's obvious in this simplified example that this one here fits both 2 and 3. And depending on how you choose it, you could find sections of curves or lines from which you could make up a wide variety of numbers. And while maybe this is an 8 by 8 or 16 by 16 image, which if it's 16 by 16 would require 250 elements, maybe we could come up with something where some much smaller set would work well for figuring out these numbers. So when we find a dictionary that lends itself to sparse representations of a given signal, those dictionary elements, or atoms, tend to reflect the structure in that signal. Well, this is a great benefit for image processing, obviously, as I've explained briefly here, but in also very many other different applications where we would like to know more than just a mathematical representation. We want to know something about the structure of the signal. So we're going to go through an optimization procedure that enables us to find D and X, where D is optimal for some given, well, we would like it to be optimal for some data set, and we can approximate finding an optimal D. And then each data element would have its own X. So let's lay out the math. First, the goal we'll find is actually a little bit hard to achieve in reality. At this time, some of you may have that fingers on the chalkboard type feel, because I just used notation that suggests that the quote-unquote L0 norm is really a norm. It's not a norm, and we can all agree that. But this counts non-zero elements of our vector x. So we want to have the fewest number of non-zero elements of x, so that y equals dx. In practice, this may not be achievable in any kind of real practical way. So we might have something like y minus dx norm is less than or equal to some epsilon. So this also is hard. It turns out this is an NP hard problem. The only way to actually come up with the best X and dictionary that would solve this for a whole data set is to try all possible data vectors or dictionary elements. And so instead what we're going to do is go after an easier goal. And this one, we're going to minimize over d and x y minus dx subject to, for every I, vector I is less than or equal to s. And so here we have y is equal to, it's a matrix y1, and I'm going to just visually show that this is a column matrix, like so. And this represents the data samples that we were given, sometimes called our training data. And similarly, we have x. It's going to represent our coefficient vectors for those respective training samples. And d is as given before. This is k by p, and then d as before is n by k. Okay, so what did we switch around? Here we're trying to minimize the difference, or we're minimizing the representation error, and subject to some absolute constraint instead of some minimum constraint on our coefficient vectors. So, how do we proceed? Well, we're going to do this in 2 steps. kSVD has, when I say 2 steps, it's actually 2 steps per iteration. We'll talk about that. One is the sparse coding, meaning the representation of our signal in a sparse sense. And so this involves finding xi, where I equals 1 to p, given a fixed d. And this xi, we want this to minimize this y minus dx. The second step is the dictionary update. So once we have found our given coefficients, can we tweak the dictionary in any given way, in some given way, so that the error continues to decrease? So given our x vector from step 1, and then we repeat. Okay, step 1. We're not going to talk a whole lot about step 1. Most discussions of this assume people know this, and maybe that's not a fair assumption, but it is a technology or approach that's been around for a long time. And so I will give you an outline of it that I think you could use, and you can also go look it up if you want more details. But let's just add this. Okay, step 1 is sparse coding. Remember, we're trying to minimize over x. Actually, we're minimizing over x and d. Let's put it all together here. Minus dx such that for every I, xi0 is less than or equal to some number s. That would be an integer, typically. But we're going to focus on just this part. That's step 1. Minimizing over this. Now, we know how to do a subspace approximation. We've already learned that in the class. If we want to do some nice subspace approximation, so low rank approximation, we can use our SVD and just pull out the first few columns, however many we want, and away we go. But that's different from a sparse representation. In the sparse representation, we actually want a bunch of the elements of each column of x to be 0. So, in order to do that, we're going to have to be a little bit smarter about this. we will essentially do a loop. Find each vector x of I. We will, let's do this, 1, find the atom or column or vector in D that best matches y sub I. That's it. How do we do this? We do this with just a projection. Some sort of a normalized inner product will tell us which one fits best. Okay. Okay. Once we've found that, then we say that y I, and I'm going to give it another index here, a lowercase n, equals yi comma n minus 1 minus alpha n minus 1 dj n minus 1. So let's add in a little more notation here. I should have given myself a little bit more room. Let's do this. Scoot this down. Let n be the iteration index. And we're going to let y I sub 0 equal yi be the iteration index there, and let alpha sub n equal dj sub n comma yi over dj n. I have squared. Okay. So with that notation, we essentially are saying, let's take our previous y, and subtract out the scaled version of the atom in D that provides the very best match. And so if we do this, we end up with our next version of y should now have a smaller norm. We're continuing to whittle away at it. So if we continue this indefinitely and our alphas were always non-zero, under a few other constraints that we won't talk about now, but in general we could see that we could eventually represent, drive the error down to 0 and have some perfect representation. But with sparse coding, we're not so interested in the perfect representation. We're interested in stopping repeat until n equals s, or some minimum error is achieved. So we want to basically just go through a few steps, and sparsity is more important to us than perfection, so we're just going to find the few elements in D that we can use to minimize the difference between our original Y and our projection. Okay, so once we've done that, then x sub I is going to be equal to a vector where most of it will be 0, but we will have an occasional alpha sub n, and my representation isn't very good there, but you get the idea. Maybe a few alphas, and these occur at the Jn locations. So in general then, we will only have S of these, and each alpha of n will occur at a Jn location. Everything else will be 0. Okay, so we do this for each x in here, and we just find out which ones fit the best. There are some variations on this if you want to look this up. This is called matching pursuits. And a variation that improves performance is called OMP, orthogonal matching pursuits. And it's a pretty straightforward thing to implement. Okay, so that's not really the innovation of kSVD. We've gone all this far and we haven't even reached that part yet. But just to provide a breakup in the lecture, this will go a little bit long. I'll pause this and start the next one, where we will discuss step 2 of our kSVD.